Hello everyone, and I have 2 midterms and a lab tomorrow. So naturally, I found myself on the Stack Exchange looking for fun math problems to do, and afterwards then spent more time trying to figure out how this new version of OneNote works, because Microsoft, it's incredibly frustrating. But anyway, let's go ahead and solve this integral right here. It's quite a little fun one. I'll leave the link down below. The first thing we're going to do actually is a good old U-substitution, so we can just say U is equal to x to the a. And this right here gives us the following. Our bounds don't change for the integral, obviously, but we do get a couple extra factors of a, so let's go ahead and take care of those first. X is just u to the 1 over a, so from that natural log term, we're going to have a 1 over a to the n, right? And then natural log of u right there. Cosine of u, obviously. And then for our dx, we're going to have a du and then over x to the a minus 1, but that right there is just going to be to the u to the 1 minus 1 over a. So we can just write it as that. So u to the 1 minus 1 over a. And we can just, we have an extra factor of u, or extra factor of a that comes from this term right here, so we can just throw that out front right there. And now we have this integral right here, which more obviously converges to some value because you see that we have, well, it's decreasing very slowly because of this natural log, but it is decreasing, and this cosine makes it dip into the negatives a bit, so it does actually converge, at least in some sense. And here we can rearrange a little bit and define this exponent right here to be some alpha, because we are going to use Feynman's trick now. So we can say that this right here is 1 over to the a n plus 1, and then we can say it's also the partial derivative with respect to alpha n times of the integral from 0 to infinity of x to some minus alpha, and then the cosine of u right here, du. Now we could do this with just the rest of the complex analysis with the cosine, but in all honesty, it is slightly easier in my opinion if we replace this cosine right here just with an e to the I u, which means that we can actually take this whole thing right here. So, bring that down right here. And then we just take the real part of the integral from 0 to infinity of x to the minus alpha times e to the iu. And then du, and close the parentheses. So now it's a matter of evaluating this integral right here, which actually isn't too bad of a challenge when we use some contour integration. So all we have to do is consider this little contour right here. So just our usual keyhole one, boop, boop, bop, bam. Love to add the arrows. There's a little dot right there. That's where our one pole is. And we have our total line integral over everything right here. That right there is just going to be 0. The only pole we have is at 0, and that's not in the contour. So, ta-da, is 0. But what this does equal is the integral over gamma 1, gamma 2, and gamma 3, and our residue is gamma 3, so it's not in the contour strictly, but you get what I mean probably. We have the integral over gamma 1 plus the integral over gamma 2 plus the integral over gamma 3. The integral over gamma 1, this is just the integral that we want because it's the integral from 0 to infinity, so yay! That's all good, so it's, we'll call that I. Gamma 2, however, is going to be slightly different. Using a branch cut, we see that this is actually, it's going the opposite direction, so we're going to throw in an extra minus. We're going to have an e to the 2 pi I. That's what you replace x with. And I'm noticing now that should not be an x, that should be a u. Same difference though. Our u becomes a u times e to the 2 pi I, which means that we get an extra factor of e to the minus 2 pi I times alpha right here. And then times I itself, which equals, well, this right here is going to be negative 2 pi I times our residue at 0. But this whole thing equals 0, so, and there's a minus right there, so just throw it on the other side. So this is 2 pi I times the residue at 0. We can factor the left-hand side in a little bit. It's nothing crazy there. What I really want to focus on is this residue at 0. We need to find, so our function, just to write it out, is e to the xi, or e to the iu, I guess, over x to the alpha. So we need to find the residue of this right here at 0, and the way we're going to do that is multiply it by some x to the alpha, right? These are going to cancel, and then we have to take the alpha minus 1th. So alpha minus 1th. Alpha. Why is it not writing? Okay, now it is. Alpha minus 1th derivative at u equals 0. And then we also have the formula includes an extra factor of 1 over gamma of alpha right here. And this right here, we can clearly see, is just going to be I to the alpha minus 1. And then just divided by gamma of alpha. And this just comes from the fact that whenever we differentiate e to the iu however many times, we're just going to get I to the however many alpha times we decide to differentiate it. E is one of the few functions, in my experience, that you're able to do this with. You have to be a bit careful, but it does actually work in this case, which is very neat. So we have this right here is a residue, which means that this right here is equal to 2 pi I times I to the alpha minus 1, but we can just kind of combine those to an I to the alpha, and then a gamma of alpha right here, which equals I times 1 minus e to the minus 2 pi I alpha. Okay, and now if you just look at this right here, we can actually solve for our integral. Sort of. Well, it's not exactly the integral we're looking for, not our integral we had at the start, but we can use it to find it. So we just have 2 pi over 1 minus e to the minus 2 pi I alpha, and then times I to the alpha over gamma of alpha. So now let's look back real fast and see what this I actually was. And you'll see that this right here was this integral. So all we have to do is, well, take the real part of it and differentiate it with respect to alpha n times. So now we can go ahead and rewrite this as 1 over a to the n plus 1 partial alpha to the n, the real part of all this, of course. Then of just 2 pi I to the alpha, but I to the alpha we can actually rewrite as as the following: e to the pi I alpha over 2. That's just because the natural log of I on the principal axis, at least, is just pi I over 2. And then we just have to divide that by gamma of alpha, and then 1 minus e to the minus 2 pi I alpha. Now, this right here is not necessarily that nice of an expression, I will be completely honest. I'm not going to go ahead and evaluate this derivative right here because I'm not even sure if there's a closed form for the nth derivative right there. However, we can evaluate it for like n equals 1, and you do get a pretty cool result if you let a be 2. It should also be noted that this right here, this whole derivative is being evaluated at alpha equals 1 over a minus 1, or sorry, the negative of that. So we can just write this as minus alpha is evaluated at that right there. So if we go ahead and just let n equal 1 and a equal 2, we find that alpha equals just 1/2. That way we don't have to switch back and forth between a's and alphas anymore. And this right here does correspond to the following integral. So the integral from 0 to infinity of natural log of x times the cosine of x squared dx. So we can go ahead and apply our formula right here. So since a is 2, we just have the real part of 1 over a squared, so that's 1 over 2 squared, so that's 1 over 4. And then times, well, the first derivative with respect to alpha of 2 pi, and then e to the pi I alpha on 2, and gamma of alpha 1 minus e to the minus 2 pi I alpha. So we can go ahead and evaluate this right here. We can move all factors of pi and like the 1/4 out front. So we have a factor of just pi over 2 out front. And then times the real part of this derivative right here. We get to use our favorite quotient rule. So we have low d high, so gamma of 1/2. And then e minus e to the minus 2 pi I alpha, or alpha is 1/2. That e bit is just going to be -1. So we just get we just get 2 right there. Low, and then d high, so the derivative of the upper bit, which is going to be pi I over 2. And then alpha is just 1/2, so we have an e to the pi I over 4. And then minus high d low, so we still have that e to the pi I over 4. But now we have the derivative of the denominator, so we have gamma prime of 1/2 right here, which that will involve some Euler-Mascheroni nonsense. I say nonsense, fun. And then we have an additional term, so gamma of 1/2, and then times 2 pi I, and then times -1. So this right here, you can just make a minus sign because of that. And then divided by the whole denominator squared. So gamma of 1/2 squared, and then we have another 2 also squared. So what this ends up being, we can obviously, the denominator is real, so we can just move that outside the real part. So we have a pi. Actually, the pi's do cancel, kind of ironically. So we actually have a 1/8 times, and then we're just going to take the real part of everything. So pi I times the square root of pi. But then we have this e to the pi I over 4. But that right there, the imaginary part of that, which will cancel with that I right there, it's just I negative I, so minus I over the square root of 2. So those i's cancel, and then we're going to have our minus. So this first term is going to be gamma prime of 1/2, which is just real, and then times 2. But the real part of pi I over e to the pi I over 4 is just going to be 1 over the square root of 2. So we have 2 over the square root of 2, which we can just write as, well, the square root of 2. And then we're going to have minus, but this minus does become a plus, square root of pi times 2 pi I. And then this term right here, to make it real, it's going to be the same thing, so minus I over the square root of 2. So the i's cancel. And this should also be a plus, actually, because that was originally a minus, and the minus canceled that minus. Okay, now we're good. So that should also be a plus. And you'll see here that this term right here is actually just twice that term. So really what we have is just a pi times the square root of pi, and then divided by the square root of 2, and then minus the square root of 2 gamma prime of 1/2. But gamma prime of 1/2 is actually just minus the Euler-Mascheroni constant minus the natural log of 4. Then we have our nice little 1/8 out front. And this right here is multiplied by a square root of pi as part of the definition or as part of the value for gamma prime of 1/2. So we can clean this up actually quite nicely if we just factor out a factor of square root of pi over 2. We have 1/8 times the square root of pi over 2 of pi, and then plus 2 times the Euler-Mascheroni constant plus 4 natural log of 2. And looking back at all this now, there actually should be an additional minus sign here. And that actually is the right answer. You might be wondering why, and this is why you always keep track of your minus signs. If you go all the way up here, you'll notice we differentiated with respect to alpha right here, and there's a minus alpha right here in the exponent, which means that there should be a factor of -1 just to the n, just a chain rule to compensate for that extra minus sign. So I do apologize, but at the end of the day, we were only off by a constant, a factor of -1, which is good. So anyway, that right there is actually the correct answer. Thank you all for watching this video, and I'll see you in the next one. And hopefully next time I record, I won't have a bunch of stuff and 2 midterms tomorrow. At any rate, see ya.